Good afternoon. Welcome to my videos on the methodologies of artificial intelligence. In this second video, we are discussing the research areas of artificial intelligence. Let me introduce myself for those who have not seen the previous videos. I'm Sergio Focardi, professor at University of Genoa, Department of Engineering, DIME, where I teach risk management and financial engineering in the management engineering course. My research activity is focused on causal artificial intelligence, creating and deploying causal models from data. Let's discuss a little bit the development of AI. Why? Well, there is no formal theory of AI. Physical theories are mathematical models that describe observations. Better, they are axiomatic systems where the behavior of any system is inferred by a small number, logically inferred, by a small number of basic principles plus descriptive conditions. The above is what is known as the deductive nomological principle. Observations are not neutral but depend on the theory. AI is different. There is no definition of intelligence on which there is a general agreement. Therefore, there is no tenable definition of artificial intelligence. If we don't really know what the natural intelligence is, we cannot really define artificial intelligence. The Turing test requires that the machine can respond to a human agent in such a way that the agent cannot distinguish the machine from the human. But this is only a relative test of intelligence, not an absolute test of intelligence. Therefore, to understand that artificial intelligence, it's useful to outline the development of artificial intelligence. There are main areas of AI research: neural networks and connectionist approaches, the expert systems, problem solving, theories of cognition, intelligent databases, cybernetics. These areas are not independent, but form a coherent development, even if in many cases there has been competition for research funds. However, we can distinguish two main strands. The first is the construction of systems that physically have a structure that resembles a human brain. The second is the creation of frameworks that mimic human cognitive behavior. So let's start with the connectionist approach. The discovery that brain tissue is made up of cells called neurons is generally attributed to the Spanish biologist Santiago Ramón y Cajal in the late 19th century. This discovery suggested that human intelligent activity is due or can be represented as due to the structure of neurons and connections. Therefore, they started to build machines. The idea was to build machines with a structure of elements whose behavior is similar to that of a neuron. In 1943, Warren McCulloch and Walter Pitts published the paper A Logical Calculus of the Ideas Immanent in Nervous Activity, in which they proposed a simple mathematical model of the neuron and the model of the nervous systems as a network of neurons. In this paper, McCulloch and Pitts demonstrated that the network of neurons can be described by propositional logic. The article demonstrated that a system considered to be as complex as a network of neurons admits a simple description in terms of mathematical logic. In 1957, Frank Rosenblatt simulated a neural network that he called perceptron. The following year, he was able to build a physical perceptron. The perceptron immediately showed the ability as a linear classifier. However, in 1969, Marvin Minsky and Seymour Papert published the famous book Perceptrons, in which they demonstrated that perceptrons are unable to recognize exclusive ORs. This book had a very negative effect on research on perceptrons. Research on perceptrons was unfunded for at least a decade. Subsequently, however, it was shown that multi-layer feed-forward networks can overcome the limitations described above. In the 1980s, George Cybenko demonstrated that neural networks are universal function approximators, and progressively research on neural networks continued. The MIT Connectionist Manifesto which is the widely recognized term for the 1986 two-volume work Parallel Distributed Processing by David Rumelart and James McClelland and the PDP research group at MIT, was instrumental to reestablish connectionism as the main research area of AI. Since then, the connectionist approach is the main tool of AI. Currently, large language models and generative approaches to artificial intelligence use evolutions of neural networks such as deep learning and transformers. But let's see what expert systems are. Minsky and Papert were accused of having caused the collapse of connectionist research in favor of the logical approach of expert systems. Expert systems consist of three main components: the knowledge base, the inferential engine, the user interface. Knowledge base includes expert-produced rules or automatically learned rules, but it's important to understand that expert systems depend on experts. The knowledge included in the rules is synthesized into systems of knowledge representation, obviously, and while the inferential engine is based on mathematical logic and allows one to ask questions to the knowledge base and produce answers. The user interface is made up of programs with which the user can interact with the system. Expert systems are among the first forms of artificial intelligence proposed. To understand how this works, consider the example of an expert system that produces medical diagnosis. In the simplest case, the knowledge base includes a large number of statements of the if-then type, which can also be linked in complex ways. The inferential engine explores these rules by comparing them with the description of symptoms and produces diagnosis using the methods of mathematical logic. More complex systems may include fuzzy logic or probabilistic notions to account for uncertainties and probabilities. Conceptually, the system is simple. There is a knowledge base in the form of rules. The inferential engine explores it and forms deductions that can be very, very complex. What appears to be complex reasoning is actually a large set of rules and the ability to explore them to form deductions. Problem solving. Problem solving is a fundamental idea of modern intelligence, artificial intelligence. In the 1950s, Allen Newell and Herbert Simon created software systems that tried to automatically prove theorems, create models, and solve problems. As mentioned in the previous video, automatic problem solving is one of the central goals of AI research. The methods proposed by Newell and Simon were based on the creation of possible scenarios with the help of various heuristics. This software showed the ability to solve relatively simple problems, but were unable to solve very complex problems. Genetic programming, proposed by John Coase in 1992, is another example of automatic problem solving. Genetic programming creates programs that solve problems. Genetic programming evolves randomly created programs using an optimization criteria according to genetic rules. Random generation of scenarios with heuristic and optimization is still the key to problem solving in artificial intelligence. Theories of cognition. Allen Newell and Herbert Simon are often considered the founders of artificial intelligence. Allen Newell developed the concept that human cognition admitted a unified explanation based on a general architecture of cognitive processes. Newell published the book Unified Theories of Cognition in 1990, where he described his conception of a unified theory of cognition. Several cognition models have been proposed, including SOAR, ACT-R, and LIDA. There are many theories of cognition today, both inspired by AI and built on psychological and social foundations. Intelligent databases. One of the most important research areas in the field of artificial intelligence is the search and management of unstructured information. Think of internet. Classical databases search for structured information. However, the search of unstructured textual information has become a key area of research, especially with the spread of internet. In the 1990s, firms such as Verity Inc. provided unstructured information search software. the amount of textual data produced was growing exponentially. Wall Street produced an amount of research that could not be managed by human readers. Pharmaceutical companies found it less expensive to repeat the research than to search the literature. Progressively, there has been a process of dual adaptation. Text search software has become increasingly sophisticated, but at the same time, the production of information has adapted to the needs of finding information by producing standard text description, such as keywords, abstract, and similar tools. Cybernetics. Cybernetics, a term coined by Norbert Wiener in 1948 with his book Cybernetics, aimed to explain human-animal behavior in scientific terms. So it belongs to the same, let's say, area of research of artificial intelligence. Cybernetics immediately presented itself as a large multidisciplinary project. Norbert Wiener himself focused his contribution to cybernetics by studying feedbacks and constructing a mathematical theory of feedbacks. Feedbacks make it possible to study certain human and animal behavior, where an organism must achieve a goal, for example, equilibrium, biological equilibrium. However, the concept of feedback is inadequate to describe complex behavior, while it has proved to be fundamental for industrial automation. The theory of automatic control is essentially based on feedback. Cybernetics has become the theory of automation. System dynamics, invented by J. Forrester at MIT in the 1950s, is based on feedback to model complex behavior. Therefore, what started as essentially a portion of artificial intelligence, in the end developed as a main, let's say, industrial tool. Well, thank you for your attention, where we explored, in this video, we explored some of the main areas of research. In the next video, we will discuss what is currently a, let's say, problem widely debated. Can we say that artificial intelligence will develop sensitivity and conscious contents? Thanks again for your attention.